Hello everybody, and welcome back to another Isaac Sim tutorial and demonstration video. In this video, we are going to be working with Isaac Sim to do some interactive cell design, and I will be going through the code that allows this to be possible. So, a common task when working with robots, especially when deploying robotic manipulators in industrial manufacturing settings, is you need to design how your cell will be laid out. Often you'll have inputs and outputs, you'll have various places that your robot needs to reach in certain ways, and that will all put constraints on how your cell can be designed. You can't just rock up and be like, oh, we'll have some boxes over there, we'll have some conveyor belt over there. There's always going to be some iteration on this, and you might have space constraints. You might want to be, have a lot of these cells tiled effectively well. You've got floor space constraints. There'll be other machines that they have to be near that they can't, run into, that sort of thing. So Isaac Sim is a really good tool for designing these cells. One reason is it's 3D, it's visual, you can drag things around and see if they work. But the other reason is because it's and you can do that in any CAD tool. But another reason is that Isaac Sim is specifically built for robotics, and so that means that you can load in robots, have them move around. There's also a and see how they would actually be performing. Um, there's also you can script other things that move around as well. Like let's say things were moving on a rail up and down here. You wanted to see if you could reach those, things like that. You can do that. There's also a big amount of pre-built assets ready for Isaac Sim that are industrial that you can leverage as well. But in this video, we're going to go over our specific example here, show some of the cool things that you can do with Isaac Sim, and show just how simple the code is actually to get this example set up. So first, I'll explain what we're seeing here. Is we've got a robot here. This is Roger. He's our ABB 10 kilogram Gopher collaborative robot, and he's set up on this 1 by 1 meter table here, and he's moving between a few example. Let's just call them stations. We got this, kind of plinth over here. There might be, some tool or something on here that he needs to be grabbing or some object. We've got some boxes here. They might be full of parts. He might either need to be emptying these boxes or putting things into these boxes, for example, and a conveyor belt. Things might be coming to Roger that he might need to take out of these boxes, out of this conveyor belt and put into one of these boxes, or vice versa. And we want to lay all of these things out in a way that the robot can easily reach them. And, let's say, it seems I just kind of dragged and dropped these in here randomly to see what it would look like. And this initial configuration seems to work quite well, but we might have additional constraints. We might not want the table coming all the way out like this. We might want to know, oh, can we rotate the table some degrees? And so we can come in here. We can find our conveyor belt in the stage tree, our conv, as it's called, and we can rotate around the Z. Let's rotate it 90 degrees. Our table's way out here. Roger probably can't reach it now. Let's see what happens when he tries to reach for that. Oh, yeah, not quite getting there, buddy. Well, you can get that side, but that's not quite where we wanted. We want things placed in the middle. We can see if we move the conveyor belt much closer, you can easily reach it now. Ooh, that's great. It's a little awkward having Roger reach all the way up here. We'll note that we're doing primitive movements between our positions here. We're not doing this as if we were doing the whole, complex path planning, collision-free avoidances, that sort of thing. But that you could totally add in here as well. So we might want to lower this conveyor belt to see if he can still do that. So we'll wait for him to come around again. When he comes around again, it'll do a solve for the updated position, and let's see where he ends up coming in and if that ends up looking better. Yeah, that's a much easier to reach to. Okay, great. Maybe we wanted to see if we could get a third box in here. We might want to rotate these 90 degrees so they're portrait as opposed to landscape, and then that would give us space for a third one, or maybe even four if we lay it out correctly. Let's see how that would work. So let's just move this conveyor belt down this way a little bit so you can see we can select it in the tree here, and then we can drag with the gizmo. There we go. Let's select our totes. We'll rotate that 190. We'll rotate the other 190, and then we can drag them around. All right, cool. So let's start with this one. Let's see if we can put it all the way over here even. Our conveyor belt looks happy. We'll see how it goes with this tote, then we'll stack this one next to it. Oh, just at the edge of reach, but it's doable. It's doable. Maybe not for the end of the... Maybe not for the end here, actually. Yeah, if he's just getting to the middle... Yeah, Roger, there's no way you can get to the end there. Okay, that's an invalid cell configuration then. So that's something we just found out. So we need to move these closer. Yeah, Roger would be able to reach to the end. If we move these out here, can he comfortably reach the middle of that? Because if he can comfortably reach the middle of that, he can get there. I messed up the order of these. Oh, that's not comfortable at all. Yeah, these need to be in as close as they can, really. I might even want to reduce the size of this table. So, move the table over there, for example. If he's on the edge of the table, there's that one. Switch the order of these, make that more comfortable. Yeah, okay, our cell's getting smaller. Much easier for Roger to reach all parts in here. Let's say we might want these on a pallet, for example. They wouldn't be flush with the floor. We can raise them up. Is that still comfortable for Roger? That might even be easier. And we'll take our conveyor belt up as well. Yeah, probably want to have it up to go into our next process that we'll be expecting at a kind of more standard conveyor belt height. And we might not want more spaces for boxes around Roger, so we can move this over here. And then we could even get 2 more boxes in here, because we saw we can get them close to Roger as long as... Yeah, something like that. There we go. And we could put 2 more boxes in here. We could also see sometimes robots, they can get better reachability when they are at altered angles. Oh, that's getting a little awkward in there, actually. Tote 1, definitely. Yeah, when we raised it up, it seems like it made it slightly more awkward. Yeah, there we go. That's nicer. Move the other tote out to match. So we don't want to be too close, and also it'd probably be hard for him to reach in on these very close positions. It still might be a little hard for him. Potentially we can adjust the robot mount like this. We could rotate that along the x-axis, potentially 30 degrees might make that easier. So he's now on an angle, and we're going all the way down to the other side of that conveyor belt. So let's make this -90. Oh, no, not like that. Don't scale, there we go. Oh no. Something looked difficult there for Roger. Or it's just getting between these two. Because Roger's solving to come around this side. He doesn't have to, but that's a bit rough. So we found out our plinth. We'll take this over here. I have a feeling that will be easy. There we go. That's much easier, isn't it, Roger? Cool. Oh, that's an awkward reach down. Tote 1. Maybe everything's too far over this way. We can take this over here. Maybe the angle of Roger as well is just a bit uncomfortable. Take conveyor belt over. Here we go. The cell is nice and compact. Yeah, that all looks very comfortable. Maybe not getting back in there. But again, this is just an example. Oh, okay, not happy there. Yeah, this 30 degree, really not happy with that. All right. Oh, I know what it is. We moved the stand. Yeah, we grabbed. There we go. So the visuals were not lining up with the actual target it was reaching for. There we go. Yeah, he's very happy without the 30-degree slant, and that makes installation easier and debugging easier, so we will leave it out. So there we go. As you just saw, in a few minutes, we rapidly went through a lot of iteration on our cell design, and we arrived at something simpler and more compact and easier for the robot to reach that also accommodates for the incoming totes to be on a pallet. We'll now go through the code that makes this possible. So we'll switch over to VS Code, and for reference, this code that I'm about to go through here, this is all released publicly at our GitHub, github.com/Workr Labs. That's with dashes in between work and R and labs /Roger-Reach. There will be a link in the description, so you can run this yourself. You can import your own assets, do your own cell designs, improve it, modify it however you need. Maybe you need some linear motions in here. Maybe you want to see how lighting affects things. Maybe you've got different size totes, different conveyors. You want it to do machine tending, or want to try it with different robots. We've got a large amount of robots available in our robots library here. So as you can see, we've got a big table of currently supporting ABB and Kawasaki robots, but we will be adding more. All right, into the code. We'll go back here. So there's not much code here. At an overview, there's 116 lines, and I will go through it from top to bottom. So at the top, we've got our standard imports. We're running an Isaac Sim standalone app. So we just import the simulation app class from Isaac Sim, and then we start a simulation app. That allows us to import the rest of our Isaac Sim functions and classes that we require, and we also have some imports of our own here. We'll use SciPy for rotation stuff, and then IK client. This is for connecting to an IK server. The motivation for having an IK client and server, as well as implementation details, were covered in a previous video, so go see that if you're interested. And then we also have our spatial utils module, which has some different functions for converting between meters and millimeters and creating transformation matrices in different axes and rotation matrices, etc. So here we got some helpers for this. Here is really the crux of everything. We want to be asking. So Isaac Sim is built up out of these things called X forms. They are the transformations, our reference frames inside Isaac Sim, and we want to know every frame. We want to know where our certain frames are, because that's what's happening here when we are moving things around. We have these things called targets, and they're just X forms. There's nothing special about them. It just means we've programmed into our code to look for certain target X forms and then read out their positions on every frame and then get the robot to target them. So I've created all of these things have kind of these wrapper X forms, you could say. We've got a tote one wrapper X form, and inside it's got our tote model, so we can visualize what things look like. And then inside it, it's got the target. The other reason for that is our target might not necessarily be the same as the origin of the model. Let's take the conveyor belt, for example. The origin of the conveyor belt model is down here, but we actually want the robot to be reaching up here. So that's why it's a child X form. So it's here. And the reason we don't have it in the world is so that when we move around the whole model, the child X form moves around as well. You can see I dragged the whole conveyor belt over here, and then the target moved here because it is relative to its parent. So that is all super useful, and it's nice that Isaac Sim gives us all of that out of the box. So this helper function here this will come back with a XYZ and quaternion, and we need to turn that XYZ and quaternion into a 4x4 homogeneous matrix to make doing math on it easy. And we've got some different helpers for wrapping that. This matrix from primpath, this is what we're going to be leveraging throughout the rest of this and calling every frame, and we can give that primpath, for example here, it'll be like /world/conv/target. We'll see a list of them down below, and then on every frame we can query, where is this prim? Where is this prim? Where is this prim? And move the robot to those prims. Next, we'll do some standard setup in isaacsim world. Then we'll add a default ground plane. That's how you get this nice blue tiles on the floor. We'll load in our scene.usd. So our scene.usd is here. I created this USD file, and that's where I defined all of these xforms and loaded in all of these assets, including like the robot mount. And this is going to be our starting point for doing our cell design. So we load that in there, and then when that loads in, we can go through and manipulate all this live. So we load that in, and then we're doing some path manipulation things down here to say, make things relative to other things. This requires knowing how you've structured your USD file. We've got a path into our robot assets library to load our CRB 1500. And we add that to the stage, and then we'll create a single articulation. This is isaacsim's way of working with kinematic trees. And then we'll put our list of target prims. So if we added a new tote, we would come in here and add it there. Like we could come in here, we could add tote 3, for example. If we came over here, we could come here, duplicate, and then this would become tote 3. And that's, and if we go, whoops, if we come find that, oh no, something went wrong. Tote 2, duplicate, there we go. I don't think I had the right thing selected. Tote 3, there we go. And now we suddenly have a third tote. So if we restarted the interactive reachability application, we could now have 3 totes to work with, for example. We could then see what would it be like to pick something up on that side of Roger. So we can come back here. This is a bit of a helper class to combine some joint radians, joint position, and a time it takes to move to that position is essentially what this data class does. These are some helpers that we're not using in this script. We've got a client to our IK, so we can do IK solves. And then we have this action generator and a while loop. So this while loop, this is the beating heart of our application. We infinitely go through our action generator and apply any actions that it gives out to us, and then we just wait for those actions to happen and then move on and generate the next action. The way the action generator works is we'll go through all of our target prims. So that's our list here. We will find out where the robot currently is. We'll find out where the target currently is, and then we will calculate IK solutions to it, and then we'll yield a series of actions. So that's our approach action. So we come up close to it. You can see here how we pause above something before we go down to it. This is standard when working with robots, and then we'll actually go down to it, and then we'll retract back up. So it's our approach action. We'll say that takes 2 seconds. Our actual pick action, for example, it takes 1 second, and our approach action will go back to that. You could also make a separate retract action if you wanted it to be different, and that takes 1 second, and then we'll go on to the next thing. This here is the crucial part of making this interactive. You could calculate these outside the loop here, but then as you drag things around, their positions would not be updated. So where the robot is moving would still be to wherever they were when the script first started. So doing this matrix from primpath, which we can see here, we create an xform prim, and then we call get world poses on the xform prim, do some quaternion and transformation matrix things, and then we end up with a transformation matrix that represents the world to robot and the world to target. And the reason we put the world to robot here in here, even though you might not be moving the robot around is just in case you are. You want to mess around with those angles. You want to, see robot higher, robot lower, robot further away. Otherwise, you're restricted to just moving your targets around. So that's why it's important to have both of these things in here. That is everything. Thank you for watching, and I hope you enjoy using Isaac Sim with its nice interface here for dragging and dropping things around for cell design, because this is super useful. We've been using it internally here at Workr Labs, and it is great. Combined with the ability to just come into the Isaac Sim editor here and just open up and say, oh yeah, we're going to put a cube in here. We'll have a separate cube here. This is going to represent, for example, let's scale this up. I'll link that. Oh, we've got some wall back here, and we don't want to ever run into that wall. Yeah, great. Now that's added to our mockups. That's added to our cell designs. You could even come into the live running one and do it here as well. But otherwise, yeah, you add it to your base, your starter set, for example, and then load in, and it's there. And yeah, your team can just quickly iterate. You can spin this up in a meeting, and work with everyone else like that, and also show it to the customer as, hey, this is what your cell might look like. You can also get some very basic ideas of what cycle times might be like as well. Thank you for watching.